Hello and welcome everyone to another episode of Maritime Innovation Updates. Today we have another interesting topic to discuss. We have our colleague Andy with us to present a very interesting underwater subject. But before we get started, I would like to inform everyone that we would kindly ask you to mute your microphones during the presentation, and also, if possible, turn off your cameras. If you have any questions, they will be addressed at the end of the presentation. Feel free to raise your hand with the hand symbol in Teams, or unmute your mic at the end. You will have the time for that. We'll give you the chance to ask our presenter your questions. Or if you prefer this way, you can also write the questions in the chat. Either way, we'll answer all of them. Yep. And with that being said, please note that this presentation is recorded. And that being said, I would like to introduce my colleague, Andy, who has joined the CML as a research associate in 2018. He has a master's degree in information and communication systems. His expertise lies into remote operation centers, decision support systems, and web application developments with strong focus on maritime collaboration and autonomous robotic systems for them. The topic for today is underwater perception for safer ship navigation. With that being the intro, I will now give the floor to my colleague Andy and wish you a pleasant presentation.
Thanks a lot,
Andy, you have the floor. Yeah.
Yep. Thanks a lot. Hi, everyone. I'm Andy from Fraunhofer CML. It's very nice to see you all here. Today, I will talk about underwater perception and how it can make navigation of ships safer. So we'll talk a bit about ourselves and then the project related to this topic. And then the use cases underwater perception can be used. And finally, a bit on our approach on how to do data collection and how it can be finally be exploited to actual usage. So our team is under the Sea Traffic and Nautical Solution Department, and we are specialized in autonomous system and nautical assistance systems. So currently, we are actively working to solve industry pressing issues and problems with our innovative robotic solutions. We work a lot with ships, but also with flying drones and underwater vehicles. And yes, so mostly they work as a team, and we hope to provide more possibilities in difficult issues. So a bit on the project, it is all about the project DTE. So this work is this project is supported by the Federal Ministry of Transportation, and the consortium consists of 4 partners. Of course, we from Hamburg and also several from Magdeburg. The outcome is the digitalization of traffic information, bathymetry, and water depth information. Maybe something about the obstacles underwater. And finally, we would like to share this kind of data, broadcast them to the roadside network infrastructure, which will be covered by our other partners. And we hope to do it in near real time. So maybe a few seconds of delay, and then we can see in a unified interface the information collected. And all these activities are surrounding the Elbe River region. And that's why the name Testbed Elbe. And yeah, with all this information aggregated and distributed, we hope to improve the situational awareness in general and more information regarding the safety and efficiency of waterway, inland waterway. So I think sometimes in the news we have saw this problem of a really low water level. So usually in Germany there are some Pegel house which will measure the water level in real time, and they will also provide some forecast in the upcoming days or hours. And in recent year, there is sometimes an issue of too low of a water level, so that it creates problems for passenger ships or ships which transport goods and materials. And it is a huge issue, because if the water level reach certain level or it is a bit low, the large ships or the captains can no longer be certain whether the waterway is safe to move the ship in. And this is one of the issues that we want to tackle. And for example, here this was from this year summer in the market board, and the water level reached a record low here. So here you see a 45. But usually this number does not strictly refers to the actual water depth where the ship can travel. Usually it's an indicator. And in this case, for the ship company, the Weissflotte, they usually require around 80 or more in order for their passenger ship to be able to travel in this region. And this also shows how important it is to have up-to-date information about the profile of the seabed. So in our project, we would like to have a ship, smaller ship, that scans the waterbed or the waterway frequently, and then we can get a very detailed profile of the seabed, and we can then give some indicator to larger ship whether they can safely move. So our approach here is to do some seabed mapping or bathymetry scan. And here are the most important concept here is the under keel clearance, or known as the UKC. And we have to always make sure the ship have a positive UKC in order they will not touch the ground. And in case they do touch the ground, then we will see a grounding accident, and usually it will give damage to the ship hull, and it is very expensive to repair. And then with more accurate bathymetry data, we also hope that this will complement the water gauge that we shown in the previous slides. So apart from the anti-grounding surfaces, underwater data can also help to address several use cases. For example, inspections, maybe the quay wall, there is some crack development. We want to keep track of whether the crack is being bigger and at what speed. Then we can do a frequent survey with bathymetry scan. And on the other hand, we can also try to detect some underwater garbage, maybe bicycles, or in some case there might be also some bomb that is undetected previously, and then we can try to use this kind of data to infer whether there's a possibility. And yes, and for this project, we are focusing on a lower TRL level of 3 to 5. Okay, now we talk about on the multi-beam echo sounding data collection pipeline. So a bit on the technology itself. For a long time, ships use a single beam echo sounder to measure the depth of water relative to the ship. And as you can see here, basically it just emits an acoustic signal towards the seabed, and then it will get a reflected signal after a certain time. And then with this time, and as long as we know the speed of sound underwater. Of course, it's sometimes not linear, and that's why we have to sometimes calibrate the water before doing this kind of survey. But at the end, with this signal, we can guess the distance between the ship or the sensor and the seabed. And in recent years, there is more use with multi-beam echo sounder. They're, of course, much more capable and also expensive. But what they do is they have multiple signals sending at different direction at the same time. So you can get a much more detailed profile of the whole line. So as well in this case. And for this project, we have used the Norbit Winghead I-80's Apogee multi-beam echo sounder, and we have mounted this sensor to the bottom of our unmanned surface vehicle, the Sea Dragon. And here you can see the basic setup of it. And the Sea Dragon is our in-house developed research platform. And then it is 5.5 meter long, and it can have a several 100-kilogram payload. And we use them to test our algorithm for sensor fusion. And in this project, the bathymetry scanning capabilities. And we also have some autonomous software running inside. So we can we want to show that with minimal personnel effort, we can complete a bathymetry scan in a manageable length of time. So here is the data collection pipeline. So starting from the sensor, we collect the signals, and then there are two software apps that handles the pre-processing. So what they basically do is to filter out the outliers and then reduce the noise, and then they will also do some sensor fusion with the onboard RTK sensor, so that they can correct the position, and at the end they can compile the whole 3D map for the area. And then at the end we will port this data into a local database, and then we will do some further processing. And then in this case, we can maybe depend on the geometry of the target ship that we are that is requesting the anti-grounding surface, and then we can compute a live map on what area in the waterway is safe for them to move to transverse. And then so this is basically the flow chart from the NAVAC software. And then with the Python, we will keep there is a script which will be run every few seconds or to 10 seconds. And then in every step, it will just read the raw data and then port them to the database at the back end. And at the end, there is a web page which will handle the rendering of the map tiles. And then it can be broadcast as an online service to the end user. So to demonstrate or to test in the real environment, we have done it firstly in the Lotse Canal region, which is just next to our office building. And then we have also collected data in the Elbe River region at 614 kilometers. So the blue box here. So of course, we have experienced some issues during data collection. So we have done a pre-test campaign at the Magdeburg region. And then we have used, instead of the unmanned vehicle, we use a motorboat there to try to do some collection and see if everything works out. And we noticed with strong water currents, and even worse, there's sometimes a lot of vegetation, some algae, some green plants floating around, which will hinder the motor, the propellers during the data collection. So this is something that bathymetry collector should be aware of. And then here is the raw data that we collected. So we have downsample them to 10 centimeters by 10 centimeters resolution. And then here is the Lotse Canal region, and here is the Elbe 614 kilometer region. So we also explore some possibilities, what we can do. And one way is to do some anomaly annotation. So maybe there are some underwater garbage or sticks or bicycles. And then we have tried to annotate them in using Blender. And then which is a bit convenient to do some 3D operation. And here's an example. So we also find out the performance-wise is also okay for real-time review. For example, you can just shine different kind of light in different directions, so the annotator can have a better overview on the whole region. And then in this case, the labeled anomalies are highlighted in red. And here, for example, we have used the circle tool to highlight several points that is most likely a car tire, which has fallen into the water. And then at the end, we can have a complete data set, which is also similar to the Kitty data set, which is from the automotive world. Yes, and this is the result. And at the end, we have a lot of red spots in the whole 3D point cloud. Okay, this is some visualization in the Blender software on how to shift this. And we also are currently trying with some AI techniques to try to do some anomaly annotation or segmentation. We try to create some training data because we don't have a lot of data currently, but with this technique, we can create a lot of anomalies and then fit into the pipeline. Okay, at the end, what we want to show is, for example, a map like this for the ships. So maybe this ships has a clearance of a few meters. And then we want to show that, for example, the red regions is no-go zone, or the yellow region is also dangerous zone, and we recommend the safe zone of which is shown in blue here. And similarly, this is the MarketBot campaign result. We also are able to show some bathymetry map, which can show that, for example, here are some red triangle, which marks some of the obstacles. And then similarly, this can be provided for the ships of whether they can transverse this region. And at the end, this all can be packaged into a web service. And as I said, be provided to the end users. Okay, so in summary, we have shown that with multi-beam echo sounder mounted on a surface vehicle, we can do this underwater scanning autonomously. And then at the future, we want to further incorporate the AI elements, and then we can do some benchmarking so that we can have more robust solution. So that would be it. Thanks a lot.
Thank you very much, Andy, for the very interesting presentation and for the insights in the project DTE. Now it's a time for questions. So if there are any questions, please feel free to raise your hand or write them in the chat, or just unmute your mic and just inform us about your questions. Until probably the first one comes, I will try to uh, sketch mine because I also found your presentation very interesting, Annie, and I would like to ask you um, regarding the time frame in which the operation, in which the maps that are rendered at the end, what's actually the time frame from the scan up until the time when the chart is available for the customer? What's the time frame we are speaking of?
Good question. So we haven't done any rigorous tests on to benchmark the render time actually, and we also just run it offline, and we didn't do it in total real time at the moment. But at the end, the data injection usually takes 5 to 10 seconds, depends on how frequent you port the data to the database. But I would say within 1 minute is a reasonable time frame to achieve this. And it also depends on, at the end, what level of detail you would like to forward to the ship owners or captain. So if you want to show the whole map, it will take, of course, a lot of time because as I shown, the raw data is around 10 centimeters by 10 centimeters. And but nevertheless, if you just want to, you can also pre-compute some statistic, which can be happen in really real time. So to forward this kind of information about maybe within 1 kilometers, what is the highest point or what is the lowest point of the water, this can be achieved within a few seconds with no issues. And then of course the rest will be depend on the network, the network connectivities. For example, if you use LTE or some other networking options, it will also create around 1 second delay, I would say at most. So I would say within 10 seconds to 1 minute is a reasonable time frame.
And basically the customer, the ship owner or the captain should just provide you with the current itinerary, and provided that the survey has already been done on that region, you can provide the output map within that minute. Is that the correct pipeline?
Yeah, whether it's correct or not is up to discussion, but I think it is a realistic assumption that we can do regular scan and then we keep updating the map. And I think for ship owners, they can also combine the profile, the whole detailed profile with the water gauge level. So then you can have already a complete view of the whole region, maybe for the upcoming 1 or 2 days. So, yeah.
Okay, perfect. Thank you very much. We have a question from Christoph Hallmann. Christoph, please.
Yes, hello, and thank you very much for the very interesting presentation. Can you hear me?
Yeah,
we can hear you.
Okay, sorry. So again, thank you very much for the very interesting presentation. And so I would like to ask you a question about mud or fluid mud that's flowing along the bottom of the river. Maybe you didn't have any issues in Magdeburg, but I assume as if you come closer to Hamburg, that could be a topic because, the sonar is so a little bit, image can be blurred by this fluid mud. So did you have, or do you have any experience with that?
Good question. Thanks a lot for the question, Christoph. So I think one colleague worked with fluid mud before on this on exactly this topic you mentioned about. But for this project, as you can see, the test we did was relatively clean, I would say, and So I think, yeah, I don't have much information on this, to be honest, but I will investigate a bit on the possibilities of do the multi-beam echo sounder for this, for this kind of seabed condition.
Okay, thank you. Maybe can stay in touch via email.
Yeah. Thanks a lot.
Perfect. Thank you very much. Are there any other questions in the chat? I don't see any. So hence, I would like to thank everyone for their presence here, and also Andy for the insights you have given us in the project DT. Because this was our last chapter or our last episode within the 2025 series, we would like to wish you happy holidays and look forward to see you in our next series, which will be starting from mid-January. You will have the schedule sent over on our website, and probably if you're subscribed to our newsletter, you will receive it in your emails. We'll continue with the first one on the 9th of January. We'll inform you on the topics and who will be the speakers for that date. But until then, have a great holiday season and see you next year. Thank you very much.